Hello students, welcome to lecture number 3 of computer architecture course. Today what we are going to focus on is on the performance analysis of computer architecture. Performance analysis is a very important aspect of any computer system. Without analyzing how we can judge the efficacy of the system, we cannot really decide what type of computer architecture is suitable for a given piece of work. Also, since we have different generations of computers coming up every now and then, it's very imperative to find out how does the computer architecture or processors evolve over a period of time. There are a set of standard benchmarks or metrics, I would say, that are there through which we can analyze performance of a computer processor. We are going to look into that today. Okay, so let's get started. So what are the different types of performance metrics? Well, performance metrics, as in like the different mathematical measures through which we can analyze performance, could be as follows, which is latency, execution time, CPU time, number of clock cycles, number of instructions, MIPS rating, so on and so forth. So as you could see, there are so many different types of varying performance metrics which can play a crucial role in analyzing the performance. But is speed and performance the same? I mean, when we refer to the word speed and when we talk about performance are both same? We'll see those things in today's lecture by asking these questions: that what is performance, what is latency, what is execution time, what is CPU time, and so on. So what is performance? Performance is a measure of how fast a processor takes to finish a given piece of task. Higher is the performance, more efficient is the processor considered to be. Okay, so we can directly measure the efficacy of a processor by the performance metric. Now, as I said, one of the most important performance metric is latency. Now, latency is a terminology that has different meaning in the context of different processors. When we are talking of general purpose processors, latency could have a different meaning. When we are talking of application specific processors, latency could have a different meaning. However, I've tried to generalize the overall definition of latency, and it could be defined as the time taken to produce the first output based on the set of provided inputs, because the set of provided inputs keep changing over time. So we cannot consider the time elapsed between providing the two different sets of inputs. Okay, it's just the computational time of the processor to produce a given piece of output. What is execution time? It is the inverse of performance. Now, performance of any processor X could be given as 1 by execution time of X. So it's inverse. So therefore, performance of X by performance of Y is N, meaning that processor X is N times faster than processor Y. If you recall the example that I had spoken about in the last lecture, we were comparing and analyzing the performance of application specific processor and RISC based general purpose processor, and I remember I determined a value that it is 246 times faster than general purpose counterpart based on certain values of clock frequency and the number of sets of pipeline data and so on. So that is that value N that I'm talking about here as well. Okay, how do we evaluate and compare the two processors' performance? There's another terminology which is known as CPU time. So what is CPU time? It is also a measure of execution time, but without considering the time spent on input output activities and spent on running other programs. Because when you're running a processor and analyzing a processor, there could be multiple programs running in the processor, some in the background, some in the forefront. However, when you want to find out the execution time, you have to consider it for a given program without considering the time spent on the other programs or any other input peripheral activities, such as how much time it takes to address an input output request coming from a printer, how much time it takes to address the input-output request coming from a USB pen drive, from an external hard drive, so on and so forth. Those things will not be considered as part of the execution time of a given program. Another very key parameter that is used is known as clock cycles. So using clock cycles to report execution time per program is also often used instead of seconds. So where frequency, that is the clock frequency, can be converted into clock cycles. So therefore time in seconds can be given as the number of clock cycles into clock period. That is the clock duration, right? Number of seconds per clock cycle, which is just the inverse of number of cycles per second, right? Which is how we define frequency. So this is inverse. Clock period is inverse of frequency. So time in seconds equals to the number of clock cycles multiplied by the clock period, which is a clock duration. So time in seconds equals to number of clock cycles into 1 over frequency. So example, if the number of clock cycles is 10 to the power 10 and the frequency is 500 megahertz, I'm just assuming a frequency of an FPGA board instead of taking the actual frequency of the processors, which is in the scale of gigahertz. Then the execution time in seconds could be given as 10 to the power 10 multiplied by 1 over 500 into 10 to the power 6, because I'm converting megahertz to hertz, and we get a value of 20 seconds. So that is going to be the execution time in seconds. Fine. Now generically speaking, we can equate a relationship between seconds per program equals to cycles per program into seconds per cycle. Okay, that is number of cycles per program multiplied by the number of seconds per cycle, and we can get number of seconds per program, which is execution time I'm talking about. Okay, let us focus on some other aspects of performance metrics. The number of instructions could affect the execution time, which is definitely something which we haven't looked upon in the previous equation. So number of instructions can of course affect execution time. Another aspect is the different types of instructions also consume different amount of clock cycles. So we have to find a way to build a relationship between the instructions and the clock cycles also in some way, because there's a huge variation in the different types of instructions consuming different types of clock cycles, different amount of clock cycles rather. For example, multiplications takes more than addition. Floating point operations take longer than integers, right? Again, floating point operations can be again of several types depending on what precision of the floating point number you're looking at. What is a exponent value, what is a mantissa value. We'll get into those aspects also in one of the subsequent lectures. Now accessing memory also takes more time than registers, so this is another aspect that can affect performance. So you see there are 5 factors here that also affects performance. So by knowing these, how can we perform better? How can we improve the efficiency of a processor? So the ways to reduce execution time or to improve performance is to reduce the number of clock cycles, to reduce the clock cycle duration, which is the clock period, that is to increase the operating clock frequency, and to reduce the number of instructions of a given program. So therefore, combining all these factors, one of the classical CPU equations can be written as CPU time equals to seconds per program equals to the number of instructions per program into number of cycles per instruction into number of seconds per cycle. And this thing collectively is known as the classical CPU equations, because they equate back to the same execution time that I was talking about. Okay, or CPU time. The CPU time and execution time are not different basically. Only thing is that CPU time does not take into account the time taken for catering to the input output peripheral activities, as well as its accessory work that it does in order to cater to the request, as well as the time taken while running other programs in parallel. So let us see another metric of performance, which is known as cycles per instruction, or CPI. So how does the instruction affect performance of CPU? CPI metric is important. A program usually has a mix of different types of instructions. So we could classify all the instructions into some specific types. Okay. So we can say that we will have a mix of several types of instructions basically. So CPI measures the average number of clock cycles consumed per instruction type, rather. The average number of clock cycles consumed per instruction, that is per instruction type, to be more precise. So CPI is the total number of clock cycles divided by the total number of instructions or instruction types in a given program. So total number of clock cycles equals to CPI into total number of instructions in a given program, or total number of instruction types in a given program. CPU time can be written as clock duration multiplied by the total number of clock cycles, right? So clock duration can be given as seconds per cycle multiplied by total number of clock cycles. So that gives you back the unit of seconds for CPU time. CPI can also be written as CPU time multiplied by the clock rate. Clock rate is nothing but the clock frequency here, divided by the instruction count. So CPU time into clock rate gives you the total number of clock cycles, right? Because CPU time is in seconds and clock rate is cycles per second. So that gives you the numerator gives you the total number of clock cycles divided by the total instruction count. So that gives you the average CPI, clock cycles per instruction. So CPU time equals to clock cycle time multiplied by the summation of j equals to 1 to small n, where small n is the total different types of instructions in a given program, and inside it we are multiplying CPI of the jth type instruction multiplied by the ij, that is a number of that jth type instruction. So clock cycle time is being multiplied by the summation function. So the one inside the summation function gives you the number of clock cycles, right? And we have clock cycle time, which is seconds per cycle, because it's actually the inverse of clock rate, which is the clock period. So clock cycle time is nothing but the clock period, right? So seconds per cycle multiplied by the total number of cycles gives you back CPU time in seconds. Okay. Okay, so let's see an example. See, imagine you have different types of instructions: ADD, MULT, CMP and SUB, and each of these different types of instructions consume the given amount of clock cycles, which is 1, 4, 1, 2, and the percentage 40, 10, 20, 30 is referring to the number which tells the number of occurrences of that particular type of instruction in a given program. That is how often that type of instruction is occurring in a given program. Or we can, or if for simplicity we can call that as the number of that particular instruction type basically in a given program. So the average CPI could be, using that summation function which I was talking about in the previous slide, the number of clock cycles multiplied by the number of occurrences of that particular instruction type in the given program. So it's 1 multiplied by 40%. That means 40% of 0.4 is the number. That many number of instructions are happening of add type in the given program, plus 4 into 10%, that is 10% of MULT type, multiplier type instruction is happening in the given program, plus 1 into 20%, which is the comparator type is happening 20% of the time, or 20% number of times rather, and then 30% is the subtractor type, that is subtractor type instructions are happening 30% of the count of the total instructions. So given by that, we find out the average CPI, clock cycles per instruction, which gives you a value which is 1.6. So this is directly evaluated based on the function that I was talking about in the previous slide, using that summation function, summation j equals to 1 to n, and then you find out the total number of clock cycles into that. Okay, now let's move to the next type of performance metric, which is known as MIPS rating. So MIPS stands for million instructions per second. Okay, this is another performance metric, and here MIPS is usually written by the following function: instructions per second into 10 to the power minus 6. Instructions can also be rewritten as cycles divided by CPI. That gives you a quantity as cycles divided by cycles per second, or cycles per instruction, I beg your pardon. So it gives you the value of total number of instructions, and then again the cycles per second into 10 to the power minus 6 divided by CPI can also be another form of writing the same equation, where cycles per second is nothing but the clock rate. So clock rate divided by CPI, and the entire quantity is multiplied by 10 to the power minus 6. So that is another measure of MIPS rating. So this could also be used as one of the performance metrics for evaluating the performance of a processor. So what does million instructions per second? It stands for instruction execution rate. The number of millions of instructions happening per second. So it's the measurement of the instruction execution rate. Okay, now let's look into another aspect of analyzing performance. It's known as Amdahls Law. What does Amdahls Law state? It states that the new execution time can be written as execution time affected by improvement divided by the amount of improvement plus execution time of the unaffected portion. Okay, so execution time affected by improvement, that portion will be divided by the amount of improvement, that is how much of improvement you're seeking for or that has happened, added with the unaffected execution time. So for example, if 70% of the execution time is done or spent on integer instructions and remaining 30% on other type of instructions, which includes 6% on floating point instructions, and let's say the total execution time is 100 seconds. So what would be the new execution time if we make the integer instructions twice as fast? So how do we find out the new time based on Amdahls Law? So the new time could be given as execution time affected by improvement, which is 100 times 0.70, because 70% of the execution time is spent on integer instructions, divided by the amount of improvement, because we said we wanted to make it twice as faster, so that's the magnitude, divided by 2, plus the unaffected execution times. Here the unaffected execution time is the remaining 30%. That includes the 6% floating point instruction. So 100 times 0.30, which computes up to 65 seconds. So we could have a new execution time of 65 seconds if we would like to make the integer instructions twice as fast. Similarly, what is the effect of making the floating point instructions twice as fast? So again, the execution time affected by improvement will be 100 times 0.06, because that's the percentage of time that is spent on floating point instructions. 6% of the execution time is spent on that, so 6% of the number, so is 100 basically, divided by, again we wanted to make it twice as fast, so the magnitude of amount of improvement is 2, plus the amount of time unaffected now becomes 94%. So 100 times 0.94 gives you 97 seconds. So the new execution time, if we wanted to make the floating point instructions twice as fast, is 97 seconds. So finally, what is the overview of performance? As we could see, or as we could make out by today's session, the execution time is the most important performance metric. Okay, and execution time, I will like to make a small note here that execution time again can have a different meaning in the context of servers, can have a different meaning in the context of application specific processors. Okay, so when we are talking of the word execution time, we should explicitly remember that this is execution time of general purpose processors, which is MIPS, that we are focusing on this course. Okay, because execution time of application specific processors consider data pipelining, which we haven't so far discussed here. Okay, we do have pipelining here, but that's not data pipelining, that is called instruction pipelining, which we'll focus in the subsequent lectures. So therefore the definition scope changes for different types of computer architectures. So the basic formula for performance is execution time equals to number of instructions into cycle time, that is the time duration of a cycle, multiplied by clock cycles per instruction. And the Amdahls Law describes how making limited improvements affects the bottom line, only making improvements in areas that are commonly used. Okay, so in today's lecture, you've understood about Amdahls Law, you've understood about the different performance metrics that includes execution time, cycle time, which is basically the duration of a cycle, clock period. You've understood the impact of CPI, clock cycles per instruction, which is the total number of clock cycles divided by the total number of instruction types. You've also analyzed the importance of the number of instructions on execution time. You've also understood the basics of latency. Okay, so by today's lecture, you should have by now understood that the execution time is the most important one. And of course, there are other metrics such as MIPS rating, such as Amdahls Law, such as using CPI, and so on and so forth, which could all be collectively combined in the classical CPU equation. Okay, thank you so much. And in the next lecture, we'll focus on the introduction to instructions, which is one of the core portions of this course, the instructions set architecture and instruction sets for 32-bit MIPS processor. Thank you.